Gustavo, can you hear us? Gustavo, are you there? Oh, now he's in the backstage. Okay, apologies for the delays. We had some technical issues, but I think we're ready to go. Our moderator, Fernanda, will get us kicked off. Fernanda, when you are ready, please go ahead.
Thank you, Shane. My camera is turned off, but it's because I cannot turn it on. Apparently, I need the host to do that. Should I go ahead like this?
If Gustavo would like to hand you host privileges, then you can hand them back.
Or it's fine for me like this too. It's okay. Maybe it might make things easier.
Sure. Yeah, please go ahead.
Okay, then. So hello, everyone. Welcome to today's ACM SIGSOFT webinar. This webcast is part of ACM SIGSOFT's commitment to provide value to its current and future members. So the ACM SIGSOFT webinar series features speakers from the Future of Software Engineering track at the International Conference of Software Engineering, as well as select keynote speakers and distinguished papers authors. I am Fernanda Madeiral, an assistant professor at the VU Amsterdam, and it's a pleasure to welcome you today. Before we get started, I'd like to quickly mention a few housekeeping items shown on the slide in front of you, or at least should be done. But apparently the screen is not shared anymore. But if you
sorry, so Fernanda, because I turned you host and I cannot share my screen if I'm not the host, so you have to give me the host privilege again.
Okay, so I just did that. But if you have questions during this webinar, please type them into the Q&A box at any time during the webinar. And then at the end of the presentation, we will have time to respond to the questions. Gustavo will answer them and we can discuss about them. So this session is being recorded and will be archived. You will receive an automatic email notification when it becomes available. So today's presentation is Cognitive-Driven Development, a Research Agenda by Gustavo Pinto, a great researcher and my beloved friend. So Gustavo is an assistant professor at the Federal University of Pará in Brazil and the head of research at Zup Innovation, a Brazilian tech company. He holds a PhD in software engineering from the Federal University of Pernambuco and has very broad interests, including human aspects of software engineering, empirical software engineering, and mining software repositories techniques. As a young researcher, he published over 100 research papers and won several awards, including the MSR Holt Early Career Achievement Award in 2022, one ACM SIGSOFT Distinguished Paper Award in ICSE 2021, and one JSS Paper of the Year in 2019. Gustavo, without further ado, the floor is yours.
Thank you for the great introduction, Fernanda. Thank you, Venera and Shane, for the invitation. And apologize all of us who are waiting for this seminar to start. And sorry again, because we have some technical issues and I have to present my presentation just scrolling through the slides. And as Fernanda said, my name is Gustavo, and it is my very great pleasure to be here with you to talk about this research topic that I have been working for the last year. And I am a white male man, and I have a picture of myself in the left. I have a gray hair, and today I hope you are seeing my back. I have this white wall behind, and today I'm using this black t-shirt. And today is less about FPA, which is my university, my dear university, and I will talk today about the work that I have been doing at Zup. Zup is a Brazilian tech company, and at Zup we really want to make Zuppers, the people that work for Zup, better at coding, at developing software. And we do believe that CDD, or cognitive-driven development, is a way to achieve that goal. And today my goal here is to talk a little bit about CDD for you and eventually inspire you to do some CDD-related research. And the motivation for this work is nothing new. All of us know that software will grow and will get old like teenagers. And eventually when teenagers get old, they raise some problems. And like software, we have to deal with these problems. We have to deal with these teenagers. Eventually, software get old to things like this. And this is, all these lines of code here are just one class. And this class comes from the Spring framework. And if you write Java code, if you happen to write web application with Java, chances are that you used Spring in the past. And this is just one class of the Spring framework, and it has more than 5,000 lines of code. And the question today is, how can we avoid this? So Spring is very popular, very well known and well used, and we still have things like this in Spring. And I do believe that we may have this and many other products and projects in the companies and in the products that we work. And I do understand that there is a whole literature of how to make software design better, how to avoid world class like this. But today I want to show up this tweet from Kent Beck, who pretty much nails this idea of CDD. So in this tweet, Beck was saying that the goal of software design is to create chunks or slices that fit in the human mind. The software keeps growing, but the human mind maxes out. So we have to keep chunking and slicing differently if you want to keep the making change. If you want to keep making change. So attention today to this phrase: keep chunking and slicing differently. And chunking and slicing is pretty much the ideas of CDD. If you want to leave this talk now, this is the main topic or slide that I want you to understand. The idea of chunking and slicing in a different way. More concretely, what is CDD is all about? So the idea of CDD is to reduce the developers' cognitive loads during the coding activities. So if we went back to that example that I just showed to you in the beginning of the talk with many lines of source code of just one class, I would say that it would be hard for developers to get that one given class and navigate between the methods and the variables and understand the purpose in a very straightforward way. They may require some time, especially from novice developers or from developers that are joining the project. And the idea, and CDD achieves these goals by posing these limits, by placing a limit on the number of items that developers could use at once. So our idea with CDD is you can use whatever you want to use in the class, but you should pay attention for this limit. And CDD, theoretically speaking, comes from two psychological theories: the magical number 7 theory that I will explain in a minute, and this cognitive load theory that I will also explain in a minute. These two theories, they are well accepted theories in the psychological domain, and we just brought this idea to software engineering landscape. So what is this magical number 7 theory? What is it all about? So the idea is that we as human beings, we are only able to process like 7 units of information in our short-term memory. We can process 2, 3, 4, 5, but maybe 7 plus 2 minus 2 are the limit of information that we can process at the same time in our short-term memory. If we receive more information at the same time, chances are that we may lose our ability to understand and process this information. So we have a figure here in the right where I can suggest that if we are processing 1, 2, 3, 4 units of information at the same time, chances are that we are able to understand, to really comprehend what is going on. But as we increase the number of information that we should process at the same time, our ability to understand drastically reduce. So when we are processing like 7 to 8 to 9 items of information, chances are that we are not understanding anything else. So this happens pretty much here when my kids are around and they are screaming and they are calling my name and they are playing with all the stuff that they have. And if I'm trying to pay attention to one thing, listen to they screaming, chances are that I will not understand what they are talking and what I'm supposed to do at work. This is the magical number 7 theory. The other theory that I want to talk to you today is this cognitive load theory. And the idea of this theory is that, you know, we understand now that we have this limit of information that we can process, but also, we also have items that, although are similar, they have different levels of complexities. So I have an example here of 2 chairs, and one chair is a black chair, beautiful chair that I can place on my living room, and that will be just fine. But I also have this green, strange, with wheels chair that I don't know if I should sit or if I should place in the kitchen, or if I should place fruits in these tabs that it has. So it's pretty much the same kind of item, but the second one makes me think a little bit more about what I'm supposed to do with this item. So the idea is that we have similar kind of items, although these items have different levels of complexities. And if we bring these 2 ideas to source code, we have pretty much our understanding of CDD. And what is CDD? CDD is this approach that we first should limit the number of items that we can use at once in one given source code file. And 2 is an approach that we should understand the items that place more or less complexities on that source code. So in the right here, I also have a figure of a simplification of a class that we have at Zup, in a product at Zup. And if you can see here in this figure, we have this ICP annotation. ICP is just a notation that we create to sum up the items of complexities that developers are using in the source code. So if you can see the third annotation from the top to the bottom, the third one is ICP 7, which says that this class has 7 items of complexities. So this is the way that people at my group work at Zup. They code, and while they code, they sum up the items of complexities that they are using in the source code. And eventually, when we arrive a limit, when we achieve a limit of the items of complexity that we are supposed to use in the source code, we refactor the source code. So this is the idea of CDD. In CDD, we understand that we should have a limit of items of complexities. And we understand also that different items of complexity, different items have different levels of complexities. And if we have more items of complexities than our limits in that given source code, we are supposed to refactor that source code. So in our case, in Zup, in our team at Zup, our limit is 10. So every class that has more than 10 items of complexity must be refactored. So this is pretty much the idea of CDD. We have the limits, we have the items of complexities, and we have the need to refactor every time that our classes are over the limit. And the beauty of CDD, one of the beauties of CDD is that the team should decide what are the items of complexities that the team believes is not good enough to use or to overuse. So if the team believes that if expressions, for loops, lambda expressions, or class that use the databases, class that uses third-party libraries, they increase the level of complexities of that source code, we should tag these items as potential items of complexities and start to sum up the number of them in their source code. So this is how people use CDD at Zup and how we believe this could help reducing the complexity by slicing them in terms of our limits. So we do have some early works on CDD that were published here and there. And today I want to talk about just two works that we did this year that I'm really proud of. So the first work is related to how CDD impact code readability. So one thing that we understand now is that, okay, CDD, it could help to reduce the size of the classes because of these limits, but does this also help to improve readability of the code? If you are moving the items of complexity to other places, we are also eventually improving the readability of the code. So this was our question for this work. And in this work, we did this kind of experiment here. In Zup, we had this code quality camp in which we invite Zuppers, the people that work for Zup, to join one Saturday morning coding camp with us. And we asked them to navigate between two open source projects. And we asked them to do some kind of refactorings on that two open source projects that we gave to them. But the point is, for part of these people, we said to them, you should do the refactorings using the CDD strategy. So CDD has these guidelines here. CDD works like this and that. And if you are trying to do any kind of improvement, refactoring the source code, your refactoring should be based on the CDD guideline. And after this morning, we ended up with dozens of refactorings that people made during the camp. And after the camp, we organized and created 10 pairs of source codes that people changed, that people refactored during the camp. And we selected 10 CDD-driven refactorings, 10 really good refactorings that people made using the CDD strategy. And we also compared these refactorings with the original version of the source code. So remember, we had two open source projects. We taught people about CDD and we asked them to do the refactorings in terms of the CDD guidelines. And then we selected a few refactorings, the good ones that we observed. And we asked them to, and we selected the refactorings and we compared the CDD based with the original source code. So now we have 10 pairs of refactorings. And using these 10 pairs of refactorings, we made a very simple questionnaire in which we asked also people at Zup which code snippet is the most readable according to our notion of readability that we gave to the participants. And on the left-hand side, we showed to them like the original version, and on the right-hand side, we showed to them the CDD version. We also made some kind of randomness on the sides of each kind of refactoring. but eventually the people just had to vote and justify their vote for the most readable version. So I like this one, I like this because this and that. We eventually had 130 something developers that answered our questionnaire. And the findings of this work is mostly based on this questionnaire that I showed to you. So I have this very brief table here that summarizes our findings. And we have here in the first column, we have the name of the change or the name of the refactoring that the people made, that supers made. And in the second column, we have the number of votes of people who prefer the original version of the source code. And in the third column, we have the number of votes of people that prefer the CDD version of the source code. And the other two columns are just the percentage. And just passing by really briefly about this work, we can see first, there is this scenario here in which there is a pretty much draw from the choice of the most readable version. Like 67 people thought that the original version was the most readable one, while 66 people thought that was the CDD version of the source code. And if you take a look at what is this particular example here, we can see that in the left-hand side, we have the original code in which we have in the first line, like saving an object into a database. And we then have this try-catch statement in which the developer was just trying to send a message to advisor with the outcome of the saving process. And in the right-hand side, what we can see is that instead of having the try-catch surrounding the send to advisor method, the developer thought that it would be better to have this try-catch inside another class, which is the send message to advisor service. So the developer creates a new class and moved this try-catch to another class. So the idea here was, again, to reduce the items of complexities, and the developer who moved the try-catch thought that try-catch would somehow increase the complexity of the source code, so it would be a good idea to move to another class. But the developers that thought that the original version was the most readable one, they also mentioned that, logging with try-catch is so easy, is so common, that for me, that does not even increase the level of complexity of the source code. So this was one particular scenario that our findings were inconclusive. We also have here, back to that table, the lines in orange are those that the CDD based versions were the most readable ones. So as we can see, the majority of the versions of the CDD versions were considered as the most readable ones. And I have here another example who was somehow similar to the previous example, but with some kinds of particularities. So like in the left-hand side, we have 1, 2, 3 if statements comparing if a variable is null. And on the right-hand side, instead of having these if statements in the method surrounding the method, we have these if statements inside a new method. So again, the developer moved the if statement to another place in order to reduce the complexity of the source code. And one of the reasons for this change was that, you know, the math of the signature is clear, and it makes it easier to understand the behavior when we are using the CDD-based version. One developer that thought that the original version was better, they said that, you know, it's important to know which exceptions should be raised. So I should look at the if and understand what is going on, what is the exception that will be raised. And finally, we also saw one case in which the original version was the most voted one in this experiment. And in this particular version, we had in the top a very simple method comparing if a variable is null. And in the bottom version of the same method, we have the use of this optional, verifying if the method is nullable, and then mapping or using these new Java features. So eventually, the CDD version reduced the number of items of complexities. In this case was the if. It reduced the number of if statements used in the source code. But on the other hand, it increased the complexity because in that case, the if statement was just a very simple thing. So people preferred the original version in that case. So in this first experiment, we understand that, you know, CDD might be a good idea for those that want to improve the readability of the source code. And then this motivated us to do another study. So we looked for readability, but how about other code quality metrics? How CDD could improve other code quality metrics? And in this other work, we did some more experiments to bring some light to this question. And in this case, the experiment was more like a case study because we used this Pandora training platform, which is a product that we are building at Zup. And it's a product for Zuper, so it's not open for everyone. And this essentially is an online training platform in which Zupers can go and train their technical skills, their soft skills during the job. And essentially, this Pandora is composed by 5 microservices, and 3 of them are written in Java. And these 3 Java services are the heart of the work that we did, because from the very first commit, they were made using CDD. So here we have 1 year of history of using CDD in a real world setting. And we also have some other services like a front-end service and a machine learning service, because as an online training platform, the students are supposed to answer the questions. And since we want to scale this up for all the company, we need better approach to grade the assignments, and the machine learning service is for that. But neither the front-end service nor the machine learning service were written using CDD. So in that case, our study is based on these 3 Java services. And what we did in that case, we mined the histories that developers left in the repositories. We also, eventually, when we had some initial assumptions and hypotheses, and we went back to the teams to double check if our hypothesis makes sense. And what I have to show to you today is basically the hypothesis or assumptions that developers agree with our data. So for me, the most interesting thing about this work is this figure here. And this figure here may be a bit hard to understand, but I will try my best to explain this figure for you. And we have here two lines. We have the red line and we have the blue line. So the red line is the sum, the average actually is the average lines of code per class in that product. So as you can see, in the beginning of the product started last year, last October. So in the beginning of the product, there are just a few classes, and these classes are really small, like 20, 30, 40 lines of code. And after some time, like after March, April, the average lines of code per class started to establish somehow around 60 or 70 lines of code. This is what it means, the red line. So if we look for the blue line is actually the number of classes that are created throughout the product evolution. So the blue line means that although we are creating a lot of class throughout the evolution, every time we create new and new and new classes, the average, the red line, the average size of that classes are somehow small, around 60 to 70 lines of code. And we ask the developers if they believe if this behavior is somehow related to CDD, and they said that it makes completely sense because of the limit that CDD places in the items of complexities that should be used in a class. So for me, that was a very interesting observation that we found. But there are also other observations that I want to talk to you. And we discussed about the size of the classes, but how about the size of the methods? So in CDD places a limit on the size of the classes, on the number of items in the classes. It does not place a limit on the number of items of complexities in the methods. It places a limit in the classes. But does it happen to impact the methods as well? So we have this paper here, really interesting paper, by the way, which the authors suggest that a good method should have around 24 lines of code. They made several analyses and statistics, and they found this 24 lines of code number, which we use it as our threshold. And we study whether whether Andorra had similar side of methods, and we noticed that 92% of the methods are under this limit, these 24 lines of code limit, which we believe is a good thing, because even though we were not actively trying to achieve this goal, this 24 lines of code goal, we eventually achieved indirectly by using CDD. And one of the developers decided that, we understand that CDD places a limit on the class, but every unit of code is impacted because we know what is the limit, what the limit is, and what goes into that limit. That was another interesting observation that we found in that study. And another and maybe final observation in the study, is how CDD impacts the testing code. So we looked for classes, we looked for methods, and we also looked for testing code. And there is this other great paper here who made a list of good testing practices. And we used some of these testing practices to understand how Andorra is close to this good testing practice. And this table here in the left is the summary of Andorra testing methods. So it has like more than 300 testing methods, and summing considering all services. And in terms of average, in terms of coverage, the coverage was a bit over 7% in terms of the first service, and a bit over 60% in the other two services. So people do test in Andorra, and we, in this part of the study, we want to understand how close Andorra is to these other testing practices. So in the paper, the author, they suggest that a good testing method should have 10 lines of code. And we noticed that Andorra has around 8 lines of code per testing method. And one interesting observation from a developer is that when we asked them if they saw a kind of relationship in terms of the size of the testing code and comparing to the production code, the developer said that, I think there is a relationship because the complexity of the test can be seen as a proxy of the complexity of the code that is under test. So since we are testing small methods and small classes, chances are that our test should also be small as well. We also did some other experimentations, like we noticed that there is around 1.2 assertions per method, which indicates that the tests are a kind of concise. And we also did not find any kind of testing method without assertions, which is also a good testing practice. So eventually we understood that CDD might help the creation of small classes, small methods, and small testing methods. But there are also other things that we don't understand much about CDD, and we really want your help to answer these other questions that we do have. So the first thing is we understand now that CDD can help in designing smaller classes. But to what extent smaller classes are better than large ones? So we understand now that we should break the classes, but as we break the classes, we increase the navigation between these classes. And eventually we have one feature that is separated between several classes. So what is the good design decision here? Should we keep this idea of small classes, or we somehow should have another understanding of limits in terms of feature, in terms of navigation, or other variables? Another thing that we really want to understand is how CDD could help developers to find items of complexities. So today, we eventually have some moments that we want to refactor the source code, but we don't know if CDD is a good idea to drive the refactorings that people make. For instance, should we blindly trust that we should refactor the CDD code that we are seeing, or we should refactor the code that we believe is more error-prone or is more complex than those that CDD is showing to us? So we don't know to what extent developers agree with our idea of items of complexities, when they do not agree with these items of complexities, and whether they would in fact refactor these items that we are suggesting them to refactor. In our first experiment, the code quality camp, we asked the developer, please do this for us. But now our question is, would developers do this because they believe it's interesting for them, or they will not do that? We still have other questions. So another question is how we could ease the CDD adoption. We have been trying to advocate in favor of CDD at Zup. We gave many talks, we discussed it to many teams. We tried to help them in many ways, but we are not that happy with the outcome of that work because people still did not use CDD on daily basis as we would love people to do. We created some tools, some static analysis tools to help people to use CDD, but we also understand that tools are not enough. Tools are not everything. So our idea is what else we should do to help people to use CDD? What kind of other technologies, adoptions, histories of success should we be inspired to help CDD be more used in Zup or other companies or in terms of research? So with this, I am going close to the end of this talk. And in this talk, we understand that CDD may help developers to write more readable code. We may also saw that CDD may help developers to design small classes, and CDD may also help developers to design small testing methods. On the other hand, we still have many other open questions like, are smaller classes really better? Do we need that small classes? We also don't understand how CDD helps developer to find and refactor items of complexities. And we also want to understand more how could ease the CDD adoption in other places. So with this, I close this talk and I'm more than happy to take your questions. Thank you.
Thank you, Gustavo, for your presentation. So we have several questions in the QA. So we're starting with a question by Philip. Do you already consider element interactivity in your ICP score? If so, how?
Yeah, good question. No, we don't. We consider only the items in isolation, but this is actually a really interesting topic for the next research.
Okay. About the first study that you presented, wouldn't selecting the good refactorings bias the final results?
Yeah, also a good question. Probably, yeah, so the main challenge here in selecting the refactorings was selecting refactorings that made small changes, like change that we can show to people in a questionnaire, not change that are made in several places at once. So that was the main problem that we're having. So the good refactorings were actually good refactorings that we could present to other people. I don't have a clear vision of what is a bad refactoring, but definitely we could look back at the data set and maybe find other bad examples, and we can discuss more if that makes sense for any of you.
Okay, still about the first study, comparing a refactored version with a non-refactored version seems to be obviously biased in favor of the refactored version. Why not compare different refactoring methods?
Thank you for the question. Yeah, we could compare two different kinds of refactorings, but since people worked on the code almost independently, we don't have the same kind of refactoring used performed by two different people. So it's kind of hard to have the same examples using different strategies. Obviously, we can set up an experiment to do this, but in our experiment, I don't believe that was easily the case. In terms of the bias, yeah, I don't know if I agree, because the idea of CDD might make sense for us, but may not make sense for other development teams. So the CDD refactory version may not be that nice for those that don't support or agree with the CDD design. So our question still is, does CDD make sense? And if that makes sense, it seems that CDD can do help, at least in this refactoring approach.
How does CDD affect code efficiency? And by code efficiency, the asker mean runtime performance.
Yeah. Good question. We don't know. We didn't make any performance experiment with CDD. My naive take would say that it may not change much, if that change would be just very small percentage in terms of time or energy or whatever measure you want to ask, because the changes that we make are very local in terms of in the first study. So they are very small changes. And I don't know if that small change would have a great impact, but just my take.
Okay, so Matthew comments that the smaller the classes, the more classes the code contains. The complexity of the software depends on both. Smaller does not mean clearer. If we make one class per method, it will surely remain small, but make it harder to understand what the software does. Shouldn't you consider composite metrics for measuring the readability of the code?
Composing metrics, I don't know if I know these metrics. If you could just suggest one of them, I can obviously use, but at this moment I'm afraid I don't know them.
Okay, so Fernando Castor asks, how context dependent is the definition of item of complexity? Is it syntactic, semantic, project-based, something else altogether?
Thank you for the question. So at this moment it's pretty much synthetic, but it depends on what the teams believe should be measured. So in that case, we measure basically coupling, branches, exception handling, and we may have one or other items of complexity that I forgot now, but are essentially synthetic items that we can easily find with static analysis tools. The interesting thing here is that people may not agree with the chosen items of complexity. So the same team may disagree with the chosen items. So like one example is that in this team, some people believe that lambda expressions should be considered as an item of complexity, but other developers do not agree with this decision. So it's pretty much what the developer team believes would increase the software complexity and is open to modify and change by every other team.
Okay, isn't CDD a complexity on its own? The developer has to keep that in mind most of the time to stay within the limit.
Definitely, definitely. So we also made some analysis on CDD-based refactorings in that product, in the history of that product. And we noticed that there are many commits that the goal of the commits is just change the annotations. So there are many commits that are just changing the number of the annotations because they figure out they did not count correctly. So yeah, so it is another complexity. I asked this for the development team, and one developer, he said that, you know, I'm just used to this, and for me, I'm doing just fine. But the other one said that, you know, it's a bit of a hassle for me, and I still have to count manually, and sometimes I forgot, and sometimes I have to do another commit just because I forgot to count the previous commit. So yeah, you are correct. We are building tools to make that easier, but since we have this wide range of items of complexities that we should counter measure, it's not the point that it's really it's hard to build the tools, but it's hard to make developers use the tools like straightforwardly, and like really integrated in the process. So this is the challenge.
Making things smaller is a harder common knowledge in development practice today. Why should we bother applying a scientific method like CDD?
Yeah, this is a good question. I don't know if I have an answer for this. But the point of CDD is that teams are supposed to do that. So it's part of the process. So it's part of the culture of the development team. If I say for someone else, hey, you should do this, they may do, they may not do. With CDD, I think one of the advantages of CDD is because people understand also that there is a limit, and the limit is clear. If I say for someone else, hey, keep that class small, what really does this mean? It may cause some confusion. And eventually, limiting in terms of lines of code, for instance, may not be a good threshold or a good metric. Our understanding of CDD is that, okay, 10 is a good limit, but it can also be 5, it can also be 20. And our more recent understanding is that it can be 10 for this kind of classes, but it can be 20 for other kind of classes because it usually handles more complexities. So why bother with CDD? I would say that CDD brings a clear vision of this limit. And if people use CDD on a daily basis, CDD becomes part of the culture.
Okay, I'm afraid we have run out of time today. Please feel free to reach out to Gustavo if you want to discuss anything further with him. I'd like to thank Gustavo again for the informative presentation and insightful answers to many questions. A special thanks to each of you for taking the time to attend and participate in today's webinar. Remember that this webinar was recorded and will be available online. You can find announcements of upcoming ACM and SIGSOFT webinars and other ACM activities at learning.acm.org and sigsoft.org. On behalf of SIGSOFT, the speakers and myself, thanks again for joining us, and I hope you will join us again in the future. This concludes today's webinar.